In section 2.3, we're going to narrow our focus of solving linear differential equations down to solving homogeneous equations with constant coefficients, also known as easy equations. You're going to love these. Your ability to solve these differential equations will boil down to your ability to solve a higher degree polynomial algebraic equation. Let's begin by learning about the characteristic equation. To solve a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus ... that pattern continues, plus a sub 1 y prime plus a naught y equals 0, where a sub I, the coefficients, are elements of the real number system for all I. So what that's saying is that all of these coefficients are constants. So we're looking at a constant coefficient linear differential equation. Now that first coefficient, a sub n, cannot be equal to 0. That's how we identify that this is an nth degree differential equation. So to solve this degree n linear differential equation with constant coefficients, we're going to make an assumption about the solution. We will let y, the solution, equal e to the rx, where r is some constant, so that the kth derivative of e to the rx is r to the k e to the rx. Now to see where that comes from, just think about repeated derivatives of y. Y prime would be r e to the rx, remember r is a constant. Y double prime would be r squared e to the rx. Y triple prime would be r cubed e to the rx, and this pattern continues. So the order of the derivative matches the power on r. So the kth derivative then would be r to the k times e to the rx. So with the assumption of this solution and its derivatives, we can substitute that into our linear differential equation. We would obtain a sub n times the nth derivative of y. That's going to be r to the nth power times e to the rx, plus a sub n minus 1 times r to the n minus first e to the rx. And this pattern is going to continue, so we'll illustrate that with the ellipsis, plus a sub 1 times the first derivative of y, that's just r e to the rx. Finally, plus a naught times y, where y equals e to the rx, equal to 0. Now remember, when our differential equation is equal to 0, that classifies it as a homogeneous differential equation. Now that we've plugged in our assumed solution and its derivatives into the differential equation, notice that each term on the left side has a common factor. That's e to the rx. So we can factor that out as a GCF, and that's going to leave behind the polynomial a sub n times r to the nth power plus a sub n minus 1 r to the n minus first power plus, continuing that pattern, a sub 1r plus a naught equal to 0. Here we have two factors multiplied equal to 0, so we need to consider when each of those factors are equal to 0. Starting with this smaller factor, e to the rx is never equal to 0. If you think about the graph of an exponential function, whether r is positive or negative, it never reaches 0. Exponential functions have a horizontal asymptote on the x-axis. So that factor will not cause the equation to be 0. This means that y equals e to the rx, our assumed solution, will work for this differential equation when r, the real number r, is a root of what we're going to call the characteristic equation. That is, when we set this factor equal to 0, we get the characteristic equation. This is a sub n r to the nth power plus a sub n minus 1 r to the n minus first plus ... plus a sub 1r plus a naught equal to 0. So let's recap that process. We started out with an nth degree linear homogeneous differential equation with constant coefficients, and we made the assumption that y equals e to the rx was a likely solution. So we plugged y and its derivatives into the differential equation, factored out the greatest common factor, observed that one of those factors would not lead us to any information about r, but when we set the other factor equal to 0, we get this equation, which is simply a polynomial equation in r. Now, one thing to observe about this equation is we could say solving the differential equation, solving the dE, is now a matter of solving the nth degree polynomial equation for r. That is, we've reduced our problem of solving a differential equation down to our ability to solve an algebraic equation. That's pretty simple. This polynomial equation is called the auxiliary or characteristic equation. Recall that the fundamental theorem of algebra states that every nth degree polynomial has exactly n zeros, though not necessarily distinct or real. So we know that we can get a solution. Got a little typo there to correct. Sorry about that. Okay, so once we solve this polynomial equation for r, we're going to have to consider some possible natures of the roots. And for the rest of this section, we're going to divide this up into distinct cases. Case 1, we'll be looking at distinct real roots. What happens if our characteristic equation has repeated real roots? What if we get imaginary solutions or repeated imaginary solutions? How are we going to express the general solution? So we'll start with the simplest case, case 1, when our characteristic equation has distinct real roots. Theorem 1 from your book states that if r sub 1, r sub 2, up to r sub n are n distinct real roots of the characteristic equation, then y equals c sub 1 times e to the r sub 1x plus c sub 2 e to the r sub 2x plus ... plus c sub n e to the r sub nx is a general solution. The expression of this general solution is dependent on what we learned in the previous section. If you'll recall, we talked about the superposition principle. The superposition principle simply states that if you have distinct solutions, then a linear combination of those solutions is also a solution to the differential equation. So what we can see here is when we solve our characteristic equation, we get n distinct real solutions. That's going to lead us to n distinct solutions of the form e to the r sub 1x, y sub 2 equals e to the r sub 2x, ... y sub n equals e to the r sub nx. Because remember, when we solved our differential equation, we made the assumption that y equals e to the rx was the form of the solution. Now, if we form a linear combination of those distinct solutions, then we're going to get another solution. That's the principle of superposition coming into play here. The linear combination of solutions is also a solution. The next question we should ask, are the terms linearly independent? Well, if we look at e to the r sub 1x, e to the r sub 2x, continuing on e to the r sub nx, if r sub 1, r sub 2, and r sub n are distinct real roots, that means they're different, then yes, these terms are linearly independent. None is a scalar multiple of the other. If we needed to, we could prove that with the Wronskian. So let's take these ideas and put them together to solve example 1. It says find the solution to the differential equation 2 times the third derivative of y minus 3y double prime minus 2y prime equals 0, subject to y of 0 equals 1, y prime of 0 equals negative 1, and y double prime of 0 equals 3. For this first example, we're going to go through all the details. So we're going to make the assumption that y equals e to the rx solves our constant coefficient linear homogeneous differential equation. So if y equals e to the rx is a solution, then we can substitute this into our differential equation. So starting with our first term, 2 times the third derivative of y, notice the third derivative of e to the rx would be r cubed e to the rx, minus 3y double prime, that's going to be minus 3 times r squared e to the rx, minus 2y prime is going to look like minus 2 times r e to the rx equals 0. As we saw with our general development of this method of solution, we have e to the rx in common between all of our terms, so we can factor that out. When we take it out, we obtain a third degree polynomial expression, 2r cubed minus 3r squared minus 2r equals 0. Now, if we set each of these factors equal to 0, we know that e to the rx is never equal to 0, so I'm not going to get any information about r out of that factor. But when we set this second factor equal to 0, we have a degree 3 polynomial equation. We can assume a maximum of 3 distinct solutions. Now, at this point, they may be real, they may be imaginary, they may be distinct, they may be repeated. Let's see what happens. To solve this, we can factor out another greatest common factor of r. That leaves behind 2r squared minus 3r minus 2 equals 0. Then we can factor this quadratic. Looks like we would get 2r plus 1, 2r minus 2. Whoops, just r minus 2. So 2r plus 1 times r minus 2 equals 0. So we're going to get 3 distinct real solutions. R equals 0, r equals negative 1/2, and r equals 2. So we do have the case of distinct real solutions. So we're going to express 3 linearly independent solutions using this format. We could say one solution, y sub 1, is e to the r sub 1, or 0 times x. Y sub 2 would be e to the negative 1/2 x. I'm just going to write it negative x over 2. And y sub 3 equals e to the 2x. Those are all 3 distinct linearly independent solutions. Since they are linearly independent, we can also apply the principle of superposition here to express the general solution to this degree 3 or this third order differential equation. So the general solution to this differential equation will be y equals c sub 1 times y sub 1. Notice y sub 1 is simply e to the 0x or 1 plus c sub 2 y sub 2. Y sub 2 is e to the negative x over 2 plus c sub 3 times e to the 2x. So our third order linear differential equation with constant coefficients has 3 linearly independent terms in its general solution. Now, you know the next part, we're going to apply our initial conditions and translate this into a particular solution. So our first initial condition given is y of 0 equals 1. Now, the second and third deal with the derivatives. Let's go ahead and find those derivatives while we have our general solution listed here, and then we'll plug in our values. So y prime, derivative of a constant is 0, so my first term goes away here. Derivative of our second term would be minus 1/2 c sub 2 e to the negative x over 2, and first derivative of our last term, 2c sub 3 e to the 2x. Let's go ahead and get our second derivative term. This is going to look like 1/4 c sub 2 e to the negative x over 2 plus 4 c sub 3 e to the 2x. Getting back to our initial conditions, the first one is y of 0 equals 1. Second one, y prime of 0 equals 0 equals -1, and y double prime of 0 equals 3. So I'm going to go ahead and set this up in matrix form. So I'm going to take the right side of these equations and translate them to the left side of the matrix. So looking at our first equation and plugging 0 in for those x's, and putting coefficients of C sub 1 in column 1, coefficients of C sub 2 in column 2, and coefficients of C sub 3 in column 3, plugging in 0 the whole time, and we set that first equation equal to 1, we get row 1 of our matrix. Applying our second initial condition, we're going to use our first derivative, and we're plugging 0 in for x. We're going to plug in a 0 here and a 0 here. Notice in this case, the coefficient of C sub 1 would be 0. We have -1/2 times C sub 2 and 2C sub 3, and we set this equal to -1. Finishing off with our third initial condition here, our second derivative, plugging 0 in for x. The coefficient of C sub 1 is again 0. C sub 2 is 1/4, C sub 3 is 4, and this one is equal to 3. So we can plug that into our graphing calculator and translate the matrix to reduced row echelon form, and we would obtain the solution. C sub 1 is -7/2, C sub 2 is 4, and C sub 3 is 1/2. We can say, therefore, our particular solution using this as our guide, y equals C sub 1, that's -7/2, plus C sub 2, that's 4, e to the negative x over 2, plus C sub 3, or 1/2, e to the 2x. And we have solved a linear, homogeneous differential equation with constant coefficients. Notice the connection between the nature of the differential equation and the nature of our characteristic equation. The order of the derivative matches the power on R. Order of the derivative matches the power on R. So that should help you when you recognize that pattern. Next time, you'll be able to essentially skip this step and go directly from differential equation to characteristic equation. The ability to solve this differential equation, once again, as you see, now depends on our ability to solve that higher degree polynomial equation. All right, let's look at our second case for the nature of the solutions to the characteristic equation. Case 2, repeated real roots. This comes from Theorem 2 in your book. If the characteristic equation has a repeated root r of multiplicity k, then the part of the general solution corresponding to r is of the form C sub 1 plus C sub 2x plus C sub 3x squared plus ... plus C sub k x to the k minus 1 times e to the rx. Now, maybe an easier way to see what's happening with this solution is to go ahead and distribute this e to the rx to each term of that polynomial. It would look like C sub 1 times e to the rx plus C sub 2x e to the rx plus C sub 3x squared e to the rx plus, and our last term would look like C sub k x to the k minus 1 e to the rx. So let's talk about where this comes from. First of all, the root of the characteristic equation was r. That's why we see the r up in the exponent position. Also, this root r has multiplicity k. So, for example, if you have a double root, you're talking about multiplicity of 2. Or if you have a triple root, you're looking at multiplicity 3. So I'm going to need k terms to express the general solution, or at least the part of the general solution corresponding to this root. If we use the subscript on the c's, we can count the terms. This is term 1, term 2, term 3, ... term k. So all together here, we have k terms. So remember, the root had multiplicity k. We're going to need to generate k terms. Now, if this were not a repeated root, then the part of the solution that would correspond to root r would simply be C sub 1 e to the rx. However, if I have another term For the second repetition of that root, c sub 2 e to the rx, well, those terms would not be linearly independent. So my general solution would be missing information. So in order to stamp out that dependence, we're going to multiply the second term by x, because e to the rx and x e to the rx are linearly independent. If I look at the next occurrence of that root, the third time that root occurs, e to the rx is again dependent on e to the rx. It's if we multiply by x, it would be dependent on the second one. So I'm going to multiply by the next highest power in order to stamp out that dependence on the previous term. So ultimately, it looks like multiplying e to the rx by an ascending polynomial in x in order that we ensure that we have linearly independent terms. And that will give us the general solution. Let's try example 2. Find the general solution of the fourth derivative of y plus the third derivative of y minus 3y double prime minus 5y prime minus 2y equals 0, given that y equals e to the 2x is one solution. So here we have a fourth order linear homogeneous differential equation with constant coefficients. That means I can solve it by determining the characteristic equation. So this time, instead of substituting the solution y equals e to the rx into that differential equation and factoring out e to the rx, I'm going to jump straight from differential equation to characteristic equation. Remember, the power on r matches the order of the derivative. So for the y to the fourth term, we're going to write that as r to the fourth. Next term would be plus r cubed minus 3r squared minus 5r to the first. Now be careful about the last term. The last term, you could think of it as the 0th order derivative. So we're going to have minus 2 times r to the 0th. Now the reason I point that out is because sometimes I have a bad habit of saying this is power 1 and I want to call that power 1. So just be careful not to make that same mistake that I do. So this is our characteristic algebraic equation. We need to solve this for r. Now, this is a fourth degree polynomial equation, and it doesn't look like it would factor by grouping or any other traditional method. But we do have one clue that e to the 2x is one solution. Well, if e to the 2x is one solution, and I look at the coefficient of x, we could see that 2 is one root of the characteristic equation. Remember, r is the coefficient of x. So if 2 is a root, then I could divide it out of this higher degree polynomial equation using synthetic division. So recall, synthetic division picks up the coefficients of each descending power of the variable. We're going to skip a line here, bring down that first. And then we're going to multiply the number in the box, the root, times the number on the baseline. 2 times 1 gives us 2. Then we add vertically here to get 3. And then repeat that process. We're going to take the number in the box, 2, times the newest number on the baseline, 3. 2 times 3 is 6, and that product goes right here. And then we add vertically to get 3. Repeating this process, 2 times 3 is 6, negative 5 plus 6 is 1, and 2 times 1 is 2, and negative 2 plus 2 is 0. Recall that in synthetic division, this last term is the remainder. So we have proved that 2 is in fact a 0 or a root of this fourth degree polynomial equation. Recall that this first line represented a degree 4 polynomial equation. After one round of synthetic division, everything on this baseline represents a degree 3 polynomial equation, specifically 1r cubed plus 3r squared plus 3r plus 1. So we can anticipate that there's 3 more solutions to this algebraic equation, and our job is to figure out what they are. One way to do that is to use the rational zeros theorem, the P's and Q's, if you learned that, to come up with a list of potential rational zeros and then test out the zeros until you find one that works. Another way to do this is to use the assistance of a graphing calculator. So I'm going to opt for the calculator. I'm going to go to y equals and type in my original characteristic equation. and take a peek at the graph. Notice that the graph crosses at x equals 2. Since it crosses, we know that that particular 0 has odd multiplicity. Also notice that the graph crosses at -1. So -1 should be another 0 of this polynomial equation. Observe also that since the graph is crossing, we would anticipate odd multiplicity for this 0. So let's go ahead, and I'm just going to tack on the next synthetic division right where I left off, stopping short of the remainder, and I want to prove that -1 is a 0. So following our synthetic division procedure here, we obtain a remainder of 0. Now at this point, the values on the bottom row represent a degree 2 equation. Specifically, if you want to go ahead and translate it back into polynomial form, you can think of that as x squared plus 2x plus 1. And you can certainly just stop and factor it directly at that point. Or if you're in synthetic division mode, you can realize, well, since the graph crossed at -1, it has to have odd multiplicity. I'm looking for a total of 4 zeros. So let's confirm that -1 is a repeated 0. So I'm going to put -1 in the box and continue my synthetic division process. So we've confirmed that -1 is a repeated 0 of the polynomial. Remember, if you get anything other than a 0 in that remainder spot, then it's not a 0, not a root. So we've whittled this down all the way to a degree 1 polynomial. So if I reassign descending powers of x starting with the first power, that represents x plus 1. Now, just because I'm in synthetic division mode, I'm just going to continue this process and show that -1 is actually a triple root. And very easily we end up confirming it 3 times. So this part is a degree 0 or a constant factor. So from our algebraic analysis, we know that the roots of this characteristic equation are r equals 2. Of course, that one has multiplicity 1, but also we found r equals -1, and this one has multiplicity 3. So we want to express the general solution to our differential equation with that information in mind. The part of the general solution corresponding to the non-repeated factor, I'm going to start with that one, will look like y equals c sub 1 e to the 2x. Okay, now the next term will use r equals -1 in the exponent position. So the next term will be c sub 2 e to the -1x. Now at this point, those two terms are linearly independent. However, because this 0 repeats 3 times, we need 3 terms corresponding to that 0. Now, if I add another term, c sub 3 e to the -x, those will not be linearly independent. So I'm going to multiply this one by an x times e to the -x because those are linearly independent. Okay, but remember, we need this one to repeat 3 times. So I'm going to need one more term, c sub 4. I'm going to multiply it by another x, so we get x squared e to the -x. So this is our general solution. Or if you want to group all of the e to the -x powers together, you could also express this y equals c sub 1 e to the 2x plus, then we'll factor out the e to the -2x, and then we have our ascending polynomial c sub 2, c sub 3x plus c sub 4x squared as its coefficient. So when you have distinct real zeros, that was case 1, you will express one term for each distinct real 0, where the real zeros become the coefficients of the x in your exponential function. When you have repeated solutions, multiplicity k to be specific, you're going to need k terms representing that repeated root, and each term contains a power of x, which causes it to be linearly independent from the previous term. Now keep in mind, you're just learning the process here. We did not prove where this analysis comes from. We didn't derive it in general, but you could certainly find the derivative of this solution and plug it into the original equation and show that this is the correct solution. Now, you may be thinking it's time to pull out that old college algebra book and review what you learned about higher degree polynomial equations, so it's probably worth it to practice one more of these. Let's look at example 3. Find the general solution to the differential equation, fifth derivative of y plus 3 times the fourth derivative of y minus the third derivative of y minus 7y double prime plus 4y equals 0. Now, different from example 2, remember on example 2 we were given one hint about one of the solutions. On this one, we're just solving it cold, no hints about any of the solutions. But because we have our convenient constant coefficients instead of functions of x as coefficients, we can solve this with our characteristic equation. So deriving our characteristic equation from the differential equation and making sure the power of r matches the order of derivative, we obtain the polynomial equation r to the fifth plus 3r to the fourth minus r cubed minus 7r squared plus 4. Now don't be tempted to put an r there. There's not a first derivative term. Y, this is the 0th order derivative, and so we're going to raise r to the 0th power here. So plus 4 equals 0. To solve this higher degree polynomial equation, this one obviously doesn't factor with the traditional method. You could either use your rational zeros theorem, your P's and Q's, or you can graph it on a calculator and make a good guess about potential zeros. So looking at this polynomial, it appears to bounce at x equals -2. Remember, when a polynomial bounces on the x-axis or is tangent to the x-axis, that indicates even multiplicity. So we know that -2 has at least multiplicity 2. Notice at x equals -1, the graph crosses the x-axis. That indicates odd multiplicity. And at x equals 1, the graph bounces on the x-axis. That indicates multiplicity 2. So I'm going to start with the 0, -2. Again, I'm looking at the x-intercept there. X equals -2, and it appears to bounce. So my hypothesis is -2 is a double root. So let's divide -2 out of our polynomial. Now be careful with synthetic division. Remember, you have to have a representative of every descending power present in your synthetic division process. We've already observed that the first derivative was missing from our original differential equation. This means that our r to the power of 1 term is missing, so we're going to need to insert a 0 coefficient there. If I don't insert that 0 coefficient, my synthetic division won't work out properly. So remember, you start by bringing down the first term and then multiply and add all the way across. When you get a 0 in that last spot, remember that's remainder 0. That means you have confirmed that -2 is in fact a 0 of this polynomial. But our suspicion is that that is a double root because the polynomial bounces on the x-axis. So let's try and confirm it again. Yep, and we have confirmed that -2 is a double root or a repeated 0. Remember that since we are starting with a degree 5 polynomial, that we can anticipate a maximum of 5 zeros. So after one round of synthetic division, this row represents a degree 4 polynomial, and we've whittled it down to a degree 3 polynomial. So we need to find 3 more zeros. Recall from the graph that we observed the graph crosses the x-axis at -1, so I can use -1 in the synthetic division process to confirm this 0. And sure enough, it works. Now I like to keep up with the degree so I can remember how many zeros that I still need to find. We need to find 2 more zeros. Don't forget, you have the option, if you prefer the algebra, you can translate this back into a polynomial, right? And then just solve that polynomial equation for x. I get going in the synthetic division mode. It's a good rhythm, so I'm going to finish out with that. The last 0 that I'm going to test out from the graph is x equals 1. We can suspect that it's a double 0 because our graph bounces at x equals 1. So I'm going to divide it out. Works the first time, and I'm going to go ahead and divide it out one more time. And it works the last time. And do observe, we have whittled this all the way down to a constant, or a degree 0 coefficient. So let's summarize our findings. We discovered that r equals -2 is a 0 of multiplicity 2. r equals -1 is of multiplicity 1. And r equals 1 is of multiplicity 2. So we want to express our general solution with these characteristics in mind. Now when I write my general solution, I like to start with the easy ones first. We'll put the complicated ones sort of on the end of our general solution. So I'm going to start with r equals -1. The part of the general solution that corresponds to that 0 would be c sub 1 e to the -1 times x. Okay, then we're going to need an exponential with coefficient -2, and we're going to need 2 terms corresponding to this one. So the next arbitrary coefficient we could use here is c sub 2 e to the -2x. But because it's multiplicity 2, we need 2 terms with e to the -2x. But remember, we're going to force them to be linearly independent by multiplying this next one by x. Okay, we'll do something similar with r equals 1. We're going to start with just e to the x, c sub 4 e to the x. And then finally, our last term, constant c sub 5, we'll multiply this one by x to make it linearly independent. So all 5 of our terms are linearly independent, and this is the general solution to our differential equation. Now, that is a great expression, or if you prefer to factor it where you can see common exponential terms, that's an option as well. So you might want to factor out the e to the -2x. You can see you're multiplying that by a linear coefficient, and you can factor out e to the x. It one also ended up with a linear coefficient. Let me give you one more option with this general solution. This may feel a little bit like alphabet soup, especially with all of those subscripts. So another option is just to use constants a, b, c, d. It makes it just a little bit more readable. So we could call this a e to the -x plus e to the -2x times b plus cx plus e to the x times d plus ex. Any arbitrary constant will do. This one's probably the easiest one on the eyes. So we've completed 2 possibilities for the roots of the characteristic equation: distinct real roots and repeated real roots. The next 2 cases that we'll examine deal with complex roots. We'll look at non-repeated complex roots and repeated complex roots. The way we express the part of the general solution corresponding to complex conjugate solutions is given by Theorem 3 in your textbook. If the characteristic equation has an unrepeated pair of complex conjugate roots, a plus or minus bi, where b is not equal to 0, then the corresponding part of the general solution has the form e to the ax, so I'm going to take the real part and make that the coefficient of x in the exponent, times arbitrary constant c sub 1 times cosine of bx. Notice b comes from the imaginary part of my complex number, plus arbitrary constant c sub 2 times sine of bx. This is related to Euler's formula, and again, we're not proving or deriving anything here. We're just learning the process. If you're interested in the derivation, you can certainly read through the textbook. So let's do example 4. Find the general solution to, we've got a 4th order linear homogeneous differential equation with constant coefficients. It's got a big long description, but it's got a relatively simple solution. So our characteristic equation in this case would be r to the 4th plus 3r squared minus 4, be careful on that last term, equals 0. Remember, this is a 0th order derivative, so it corresponds to r to the 0th power in our characteristic equation. Now, this one's factorable. We don't have to do our synthetic division on this one. We can factor this as r squared minus 1 times r squared plus 4 equals 0. Breaking down that first difference of two squares, we obtain factors r plus 1 times r minus 1. And sum of two squares here will not factor. So we're going to get 4 zeros or 4 roots. R equals -1, R equals 1. And when we set this last one equal to 0 and we solve for r, we could use our square root property here. We would obtain plus or minus 2i. So we have two distinct real solutions and a pair of complex conjugate roots. For our first time around here with complex roots, it might be easier to think of these as 0 plus or minus 2i. So I can see both the real part and the imaginary part. So we will express the different parts of our general solution based on the rules for the nature of particular roots. So I'm going to start, of course, with the easy ones. Those are the distinct real roots, starting with r equals -1. And I'm going to opt for coefficients a, b, c this time. So corresponding to r equals -1, the part of our general solution would be a e to the negative x. Corresponding to the root r equals 1, we could express that as b e to the x. Now here's the new part. We are going to follow this new pattern to work with our complex conjugate roots. So we're going to have plus e to the ax. A in this case is the real part of my complex solution, 0x, times, now I just need an arbitrary constant here. I'm just going to use c times cosine of bx. Remember, b is the coefficient of the complex part of our solution. So c cosine 2x plus d sine of 2x. And of course, we could simplify that a little bit. A e to the negative x plus b e to the x plus c cosine of 2x plus d sine of 2x. So these are very straightforward and easy to solve, but you do have to put a little bit of effort into memorizing the different cases. What do I do with distinct real roots? What about repeated real roots? How do I express the part of the general solution corresponding to complex conjugate roots? Once you have those basic patterns memorized, then these are really easy, user-friendly differential equations. Now, just think about where we've been. This is easier than, for example, solving something with an integrating factor or some kind of substitution. What makes this section so easy? We're dealing with constant coefficients as opposed to functions of the independent variable for coefficients. Now, before we look at this next example, I want to remind you of a couple of formulas from hyperbolic trigonometry. Hyperbolic trigonometry yields ratios and identities derived from a unit hyperbola as opposed to a unit circle. Now, if you don't know much about unit hyperbola or hyperbolic trigonometry, I encourage you to Google it. You'll be surprised that there's a whole different branch of trigonometry based on a unit hyperbola as opposed to a unit circle. The 6 hyperbolic trig functions can be related to exponential functions as well. Here are 2 of our hyperbolic trigonometric functions, the hyperbolic sine and cosine functions. Notice we denote these with an h next to the name of the trig function. So this is hyperbolic cosine of x and hyperbolic sine of x. Hyperbolic cosine of x is defined as e to the x plus e to the negative x divided by 2. And hyperbolic sine of x is e to the x minus e to the negative x divided by 2. So sine is the one that is associated with the negative. This happens in a couple of different identities, and the way that I remember that sine gets the negative is related to the word sin, right? Sin is bad, sin is negative. So sine always gets the negative, cosine gets the positive. There's a couple of different identities that follow that pattern. So let's try example 5. 1. Find a linear, homogeneous, constant coefficient equation with general solution y equals a cosine of 2x plus b sine of 2x plus c times hyperbolic cosine of 2x plus d times hyperbolic sine of 2x. Did you notice that we're working backwards here? We're starting with the solution to the differential equation, and based on the nature of the terms, we want to work backwards and figure out what was the original differential equation. Now, to do this, I'm going to begin by replacing hyperbolic cosine and hyperbolic sine by their definition in exponential functions. We'll replace hyperbolic cosine using this formula. Now, notice the argument of my hyperbolic cosine is not x, it's 2x. That simply means that everywhere I see an x in the formula, I'll replace it with 2x. So we end up with e to the 2x plus e to the negative 2x divided by 2. And we'll do the same thing with hyperbolic sine. We'll replace this with e to the 2x minus e to the negative 2x divided by 2. Based on the terms, we want to figure out what were the roots of the characteristic equation. So looking at the first two terms, I'm going to add one detail here. Since we have a cosine and a sine, that corresponds to a coefficient of e to the 0x. Thinking about what we learned about complex conjugate solutions. Now, it's not absolutely necessary that you write the e to the 0x over there, but I'm doing it for instructive purposes. Now, I also want to collect my e to the 2x terms. So I notice in the first parenthetical expression there, the coefficient of e to the 2x is c over 2, and in the second one, the coefficient is d over 2. That way I've just combined like terms here. I'm going to do the same thing for e to the negative 2x. We have c over 2 minus d over 2 times e to the negative 2x. Now, based on the nature of this term right here, we can see that that corresponds to a complex conjugate pair of solutions 0 plus or minus 2i. Also, from this term, because of the exponent on x, the coefficient of the exponent there is 2, we get a distinct real solution r equals 2. And from this one, we can see distinct real solution r equals negative 2. From the roots, we can now backtrack to the characteristic equation. I'm going to start with the easy ones, the distinct real solutions. If r equals 2 is a root, it came from the factor r minus 2, right? If r equals negative 2 is a root, it came from the factor r plus 2. We can even do the same with our complex conjugate pair, r minus 2i and r plus 2i. Remember, our characteristic equation is equal to 0. So if we do a little bit of algebra here, foiling the first two binomials, we'd end up with r squared minus 4. And foiling our second two binomials, we'd end up with r squared plus 4. One more round of FOIL gives us r to the 4th minus 16 equals 0. Now, if that's the characteristic equation, we can say, therefore, the differential equation, dE, is the fourth derivative of y minus 16y equals 0. Remember, the power on r corresponds to the order of the derivative. So right here especially, you have r to the 0th power, so you're looking for a 0th order derivative, and that just gives me my y term. So working backwards from solution, we were able to determine what the original differential equation was. So we have one more case for the roots of the characteristic equation. This is the worst case scenario, repeated complex roots. Now, theorem 2 holds for repeated complex roots. If you'll remember, when we had repeated real roots, we stamped out linear dependence by multiplying by powers of x, ascending up to the multiplicity. Whatever the multiplicity of that root was, that's how many terms we need. And we would introduce a power of x with each new term. Now, if the conjugate pair a plus or minus bi has multiplicity k, then the corresponding part of the general solution has the following form. E to the a plus bix corresponds to 1/2 of that complex conjugate pair. e to the a minus bix corresponds to the second half of that complex conjugate pair. Notice you have a polynomial in ascending order, and the purpose of that is to get rid of any sort of linear dependence or duplication. Now, earlier I mentioned Euler's formula. That helps us to expand this exponential with that complex coefficient into a term that looks like this. So you'll recognize this as matching what we just learned about complex solutions. If the real part of our solution is a, that gives me the coefficient of x on my exponential term, and if the imaginary part is b, that gives me the coefficient of x on the argument of my trig function. So I can see that term there. Now, looking at it in this condensed fashion, again, what we're doing is simply multiplying each new term by a power of x in order to get rid of linear dependence. We won't see this case very often, but it is worth mentioning. We're going to work backwards again on example 6, and we're going to put all the information that we learned together in one problem. Suppose the roots of the characteristic equation for a differential equation are 3, -5, -5, 0, 0, 0, 0, -2 plus or minus 3i, and -2 plus or minus 3i. Let's find the general solution. Well, we're not getting our original differential equation. We're just going to jump straight to the roots of the characteristic equation and make sure that we know how to express the general solution. So let's start with our easiest roots first, that is distinct real solutions, and then we'll increase in complexity as we develop our general solution. So notice here, 3 is a distinct, that is non-repeated real solution. So the part of the general solution corresponding to that root would be a times e to the 3x. Now, the next two roots are real, but it is repeated twice. So we're going to need be to the -5x, but we're going to need two terms corresponding to -5. For the second term, we're going to multiply by x to make it linearly independent. Then we have the real 0, 0 with multiplicity 4. So we're going to need d times e to the 0x. Remember, 4 terms corresponding to r equals 0. E times x, e to the 0x. Remember, x makes it linearly independent from the previous term. F, we're going to need another multiple of x here, x squared, e to the 0x. And then one more power of x, x cubed, e to the 0x. So to organize our terms here, these two correspond to r equals -5, and these 4 terms correspond to r equals 0. And of course, that first term is r equals 3. Now, what to do with the repeated pair of complex conjugate solutions? I'm going to do my ... here because I'm afraid I'm going to run out of room and continue my general solution here. We're just going to start with the first one. The real part is -2, so we know the a from our complex conjugate pair. The real part becomes the coefficient on x in the exponent of my exponential function. Then the imaginary coefficient, e, f, g, h, we're running out of letters here, becomes the coefficient of the argument of our trig functions. So we have h cosine 3x plus I sine of 3x. But because this complex conjugate pair is repeated twice, we're going to need another term. And to make sure it's linearly independent from the previous term, we're just going to multiply it by a power of x. X to the power of 1 will do. So let's see, what's our next letter? J cosine of 3x, k sine of 3x. So this part of our general solution would correspond to r equals -2 plus or minus 3i. Let's take one last step to simplify and clean up this very large general solution. Starting with a e to the 3x. On the next two terms, we could factor out e to the -5x. Its coefficient would be b plus cx. Now, for the next 4 terms, e to the 0x equals 1. So we just need to record the corresponding polynomial. I'm going to group it together in a set of parentheses to set it off. D plus EX plus FX squared plus GX cubed. And then I'll keep these two terms as they are. That's the simplest expression. Barely fit it in there, snuck it right in there. So that would be the general solution with a set of roots corresponding to a very large characteristic equation. So in this section, you learned how to solve linear, constant coefficient, homogeneous differential equations using a characteristic equation. You've got 4 possibilities: distinct real solutions, repeated real solutions, complex conjugate solutions, and repeated complex conjugate solutions. Make sure you know how to translate the nature of the root into the corresponding part of the general solution. In the next section, we'll look at applications of equations with these types of solutions. Thanks for listening.